All right, welcome back everybody for the second part of this video on a 2D axisymmetric analysis of a pressurized cylinder. So in the previous video, I showed you how to set up the analysis and run the analysis. And now we're going to interpret the stress results and compare them to some hand calcs. So for a pressurized cylinder, the stress equations are relatively simple. These are out of Shigley's Mechanical Engineering Design. And for a thick-walled cylinder, I have here the equation for the tangential stress or the hoop stress. So that's the stress acting in the tangential direction in the cylinder, or in this case, theta, and it's commonly referred to as the hoop stress. And then I have the equation here for the radial stress in the cylinder. And for this case, I've assumed that there's no pressure on the outside of the cylinder, and it's only an internal pressure. So for that case, the stress is a function of the applied pressure, the outer radius dimension, and the inner radius dimension. Now, to calculate the max shear stress, we've learned that it's a function of the max principal and min principal stress. But for this case, since there's no axial stress, the max principal stress is going to be our hoop stress, and the min principal will be our radial stress. So to calculate the max shear stress as a function of radius, it's just the difference of the hoop and the radial divided by 2. Now there's a special case for thin wall pressure vessels where if your radius divided by your thickness is greater than 10, you can make a thin walled assumption, and the equation is PR over T for your average hoop stress, and the radial stress gradient is very small. So if we go back to our results, I have plotted the normal stress here. In this case, it says the x-axis, but this is for our 2D axisymmetric case, it's the radial stress. And then I have here the hoop stress, which in this case is the z-axis. And then again, I've created the path, which I've shown you how to do in previous videos, on the edge of this part. And I've mapped the radial stress and the hoop stress to the path. And then I also have the maximum shear stress here plotted. And if you want to just verify that, I can show you that the maximum principal stress is equal to the hoop stress. So if I go down here, if you look at the max paren and you look at the max and min values, you'll see that it's the same as the hoop stress. And then likewise for the minimum principal stress, if we look at our radial stress. So the radial stress is compressive stress, and the hoop stress will be tensile in this case. Again, that's what the pressure applied on the inner radius of the cylinder. And then I have mapped the maximum shear stress to the path. And so I plotted the hand calc results versus the ANSYS FEA results. And as we would expect, they agree You can see here that the hand calc is shown uh, with the circle marker, and the ANSYS FEA results are the square marker. And you can see for our hoop stress here, they line up, and likewise for our radial stress, and also for the max shear. Now, I should mention that if you have a exterior pressure, you have to use a different equation here. And maybe I guess I'd give a reference to Shigley's mechanical engineering design. If you have a external pressure and an internal pressure applied, you need to use the full equation for that. Again, this is the simplified equation where the pressure is only acting on the inside of the cylinder and no pressure is applied to the outside of the cylinder. So yeah, thanks for watching, and looking forward to making more videos for you guys.